So this is just a quick concept bite about the very basics of transient absorption spectroscopy. Transient absorption spectroscopy is a kind of a more general term for a number of different techniques in terms of wavelength, but are all using the same fundamental concepts. So you occasionally hear terms like pirate, which is just a version of infrared transient absorption spectroscopy in the picosecond time regime. What I teach you for one is applicable across all things. Now, transient spectroscopy is slightly unusual in terms of we're actually interested in what's going on with the excited state of the molecule, but we're using absorption to look at it. Normally, if we're thinking about excited states, you normally think about fluorescence, but we're looking at absorption. And so my spectra have both negative and positive parts, and I'll explain those later. But one of the most important things is that we look at it, how this absorption evolves over time. And so it's a time-resolved technique, unlike the dichroism spectra that we did before. So the basic method of transient absorption is incredibly similar to an experiment that you've potentially done in the lab, and that's the flash photolysis experiment. Porter's experiment on flash photolysis is absolutely the precursor. The difference being Porter looked at one wavelength, and usually with transient absorption spectroscopy, because it's got the word spectra in it, we're actually looking at a whole selection of wavelengths together. But that means that the basics of Porter's instrumentation are exactly the same. I have my sample cell, and I have two sources of light. I have one which is my probe light. That's the one that's kind of like my regular absorption light, as I would have had before. But in this case, I also have a pump. The pump is orthogonal to the probe light source in basic instruments, although as I move to faster instruments for reasons to do with how the spectroscopy behaves, I'm going to use a magic angle. We'll see that later. But orthogonal is common in slower speed instruments, nanosecond instruments. And I just have a simple monochromator and a detector. Detectors commonly were PMTs, they're increasingly CCDs. And I can measure my spectra in two different ways, either a kinetic mode, where I look at a single wavelength and look at how the signal develops over time, or in spectral mode, where I look at a fixed time delay and measure the whole spectrum. Now, as I said, 90 degrees works for some, but if I go to ultrafast techniques, my instrumentation looks different and my angle that I excite at is different as well. So this is a schematic of an ultrafast femtosecond type system. And in this case, my source and my scanning signal and my pumping signal, my probe and my pump, are the same laser source. So I'm using the same laser source, but if I want to get any time resolving information from my technique, what I'm going to have to do is delay the signal from one of them getting to my sample. And in fact, I delay the probe light. So I generate my excited state using my pump light, and then I basically taking an image, like with a flash camera, a certain amount of time afterwards. This case, the angle I use is the magic angle. That's to avoid any anisotropic effects. And almost certainly in modern instruments, the detector is a CCD-based detector. Now, the laser is an unusual one in that we're saying that we can look at lots of different wavelengths, but then I'm using a laser which is monochromatic. And the reason I can do that is I can use a continuum generator. This is normally a Thai sapphire crystal. And it will generate a white light source from the near UV all the way well into the infrared. 1200 nanometers is not unusual. So what's the technique actually looking at? Well, essentially, when I measure my transient absorption, the signal that I see in the processed data is the change in absorption between that particular time and before I excite my sample. That means that it appears that I have positive parts of the spectrum. That's where the absorbance of the excited state is observed, and I see a negative part of the spectrum where I see a bleach of the ground state, a loss of the ground state. I see a loss of the ground state whenever I make an excited state. Usually if we use just absorption spectroscopy, one of the key factors is that the amount of light absorbed has to be low. It's because I don't want to see any effects of seeing an excited state in my absorption spectra. In this case, though, that's specifically what we're looking for. Determining things like the extinction coefficient of the excited state is not easy, although it is possible. You can run calibration data. The important thing, though, is usually just picking out particular wavelengths of transitions, or even just picking out the fact that these transitions occur with certain lifetimes. We can spot how the energy moves around a molecule or is transferred between two molecules as we look at how these signals develop over time. I've just kind of made a quick schematic sketch of a potential transient absorption spectra here. Here, my spectra is evolving, so the time is progressing as my signal moves from dark to light. I've drawn arrows in the direction of how things evolve with time. This is again normal practice because usually you get a lot of overlapping lines. I can see in this spectra that although I instantly see the bleach, this is the part below the spectra, moving from dark at the bottom to light at the top, I also see loss of ground state later on. As it moves, I get the light signal just at a slightly higher wavelength. This is indicating energy is moving around either within the same molecule or is being transferred between different molecules in my system, perhaps a donor and an acceptor system. Spectra can be really complicated, but usually just trying to analyse what happens at certain times, what times, periods these processes are happening on. Are things happening on a femtosecond, a picosecond, or a nanosecond scale? Nanosecond would usually indicate something along the lines of either chemistry happening or fluorescence. It's been a stable excited state, whereas down in the femtosecond, often things are still reorganising themselves. But we have learned that we can still see emission or energy transfer from these excited states, even though they don't obey Cash's rule. I hope this has been helpful. I'll be back with more.